Okay, hello. Welcome back to this new stream for the OpenHT PCB. And I again messed up my audio. Amazing. Okay, better like this. So yeah, let's go on KiCad already and have a look maybe at the schematic, the few things that changed since last time. So if I remember correctly, we mostly added divider bridge, resistive divider bridge, in order to be able to measure the battery voltage. So we plan on using a 2 cells lithium battery, so between 6 volts and 8.4 volts maximum. And so yeah, we needed this dividing ratio in order to be able to fold it down to the measurable range of the nuclear board. We also, so now the V-in of the nucleo is not connected to the battery voltage directly. And if we go have a look at the power supply part, we now have this one, which is basically a power switch connected to the output of the power button controller, so this one. Which means that when the device is off, the nucleo board doesn't receive any power either. So yeah, it was not the case previously. So previously, if we had the battery connected, it would always power on the nucleo board. Okay, so now that this is done, those few additions haven't been routed on the board yet, so this is still to be done. Here is the transceiver part, which didn't change, and on the FPGA part, mainly a few commands were updated. So yeah, and we are maybe gonna already modify it again, because we planned on renaming IO4 as the soft reset. So I don't know which name we should give it, but this is gonna be, yeah, the button that you, the pin that you use in order to reset all the logic behind in the FPGA, so the internal registers and so on. Okay. So yeah, I'll just have a look at what we discussed previously on the OpenHT channel on the M17 Discord. It was a few days ago. Yeah, FPGA, let's call it FPGA RST. And then this one is IO4, IO5, IO6. So this command needs to be updated too. Like that. And of course this. This also needs to be updated. And maybe we are gonna move those around too, so that there is no, yeah, it makes no sense for it to be this way. And this one needs to be 4, 5, and 6. Then FPGA reset. Same thing here. IO4. IO5. IO6. Reset, and then the wires in between. Perfect. So this also needs to be renamed. Like this. Okay, great. So let's go to the board file, this one, and let's import the changes already. U204, what was this one? Yeah, doesn't like to have a window open. Okay, it complains that it doesn't find the correct pin number for that one. What is the problem? Hey, what did I? Oh, okay. Oh la la la. Yeah, U204 is this one. So it's supposed to have a 7th pin. How is that? Not sure I understand everything. Oh, it does have a hidden 7th pin. Oh, I guess it's because yeah, okay, I think it's because it's supposed to be in another package initially, which has 7 pins, and the one that we use only has 6. So we might have to copy that into the KiCad 17 library and remove that one, because we won't be able to. We shouldn't, at least, modify it in the standard KiCad library. So okay, let's do that quickly to get rid of this error. Okay, and always have a few freeze. Not a problem. So okay, can we edit library symbol? So we can just copy that. Then M17, we are gonna go into M17 power and paste the symbol. Remove the 7th pin. And also GRV, and I think we need to modify the value, because the value depends on the package that we use, I think. So let's have a look at the datasheet of the components and see together what we can find. So layout, this is, so we see that there is only 6 pins on the SOT package, but there should be, yeah, okay, so there is SOT23. No, I don't get it. All packages are supposed to have 6 pins, but the one in the library does have 7, which is weird. Supposed to be a ground pin. Maybe there is a bug in the library, actually. So, so it's the DRV, and DRV is indeed the WSON package. Okay. Well, let's not bother too much. We can delete it, save it, and push the changes already on the library, which is gonna be in this library. Open submodule. Okay, and so now we can just change symbol and go pick the one from the M17 library. And so you notice that the value that we have typed here is dBVR and not DVR, DVB. So I think there are 2 letters which are reversed. It's just supposed to, it's the same component except that one is supposed to be able to carry 2 amps and the other one is supposed to be 3 amps. But we are never gonna reach even 2 amps, so we don't really care actually. We are just gonna go for whichever is the cheapest. So that is done. Let's save and let's trace the board already and go back to the PCB and import the changes. No net found for symbol. U204 pins. Huh? It's not the correct pack. Ah. Yeah, okay, so this package does have 7 pins. Interesting. We just didn't change the value, so we need the SOT. Yeah, TOSOT, so SOT 236, that one. Okay, and now, okay, good. We also had to tune the length of the differential pairs, and so we have to modify the wiggles, the famous wiggles, in order to, yeah, what if want it to be all the same length for 35 millimeters. So okay, let's do that too. And so target length 35. Let's see if we can do it just like that. Okay. Okay, so now it's tuned to 35 millimeters, all the pairs. So, okay, this is great. Now, the thing is, so if I take the board, last time we decided to update, yeah, maybe it was not on stream, but we decided a few days ago to change the SMA connector length value to something for which which will be, this one is smaller, so I can show you what it looks like. This one. So yeah, we decided to change because it was more compact in terms of, yeah, the opening that we would need to make in the case, the 3D printed case for the proof of concept will be, it's much better if we have a round opening than a square one. And so we decided to go for another value component. We found this one for which we designed the footprint. And given that the 3D step files aren't license free, K5JAEJ decided to do a 3D model for it. So thank you very much. Because we now have an accurate 3D model, basic but accurate nonetheless, 3D model for the SMA connector. So now we are gonna place, so this is gonna be the top of the board when we hold it like this. So the SMA connector is gonna be right here, above the micro USB. The mini USB is gonna be on the bottom, and that way if we want to use it to power the boards for the proof of concept, then we are not gonna have the antenna and the cable at the same place, which is gonna be much better. And yeah, we now have to place the button so that J can go on the 3D case. And we intended on doing it smartphone-like actually. So meaning that we would have on the thumb the power button and on the index the push to talk button. So that would make it so that the board is going to be this way if we look at the screen. And so we would need the power button to be around here and the push to talk to be around here, and also be around where you would place your thumb. Those are low profile buttons, so we can basically stick them anywhere we want, except on the connectors, of course. So I guess about here would be nice. I'm gonna so if I take the the Nucleo board like a smartphone. The thumb naturally falls kind of on the top of it. So let's have a quick look. I'm gonna go grab a caliper actually. So yeah, let's try to measure where the finger go on the board naturally. So that would be a bit. So just trying to do a rough measurement. It would be about 3 centimeters from the top, maybe a bit less, so 25 millimeters from the top. It would be quite convenient, I guess. Yeah, and for the push to talk, we can either put it, yeah, it would make sense to do it at the same level actually. So it would be 25 millimeters from the top for both. So if I close the 3D viewer, then we can have this one. So this one, which one is it? It's 201, SW201, which means that it's the power supply one. And then this is the push to talk. So yeah, okay. So that means that the power supply one needs to go there, and the push to talk one need to go here. But they need to go on the bottom of the board. And 25 millimeters from the top. So let's place the mouse right here, is at the coordinates, and look what 25 millimeters is. Yeah, we are not exactly 25, but close enough. Maybe we can use a like this. Okay, right here would be nice. So but I want this to be okay, perfect. Okay, and so can we use a smaller grid now and try to put it closer to the edge? Or can we? Because this is gonna be a hole, I think. So that means that, yeah, we don't want a hole too close to the edge of the board. Hey Bastien, yeah, stream popped up. Doing for until about 5 p.m. Let's say, doing few KiCad layout things. So we are placing basically the buttons for the power supply and PTT of the proof concept. Yeah, let's look at either the minimum clearance between a hole and the board's edge. I guess we are still not 100% sure that we are gonna go with Acer for the manufacturing. But yeah, I guess their requirements are quite standard. So that would be M, I guess. PCBH to pad. That's weird. They don't give. Yeah, okay. NPTH to NPTH is 250 micrometers and PCBH to pad is 300, so it's coherent at least. So yeah, let's have a look how close we can get it without crossing the 300 micrometers line. Yeah, okay, so we would need to put it okay. Yeah, but this would be very close to the edge, very far from the edge, and we don't have the room needed to push the button. What clearance do we have now? It's gigantic. I don't get it. So like this should be enough actually. Yeah, this way we have 300 microns. Okay, this should be enough for us to push on the button, and so yeah, we have the button should go over the edge by at least the length of its course. But also I think Jay is gonna design us cutouts in the 3D model so that we can have a kind of a flap which is gonna press on this button, so it should be easy to use when using the 3D case. Okay, and now is it? Wait a minute. It's on the wrong side of the... Oh, how dumb. So it's actually on... The board is flipped 180. That means this need to go here and not there. Oops. So now we need speak fine grit and measure 25 millimeters. 24.99. Yeah, okay, good enough for me. So right here, this one, like that, and this will need to be okay, like this, and also the clearance, so we can move it by 2 increments, yeah, like this, and we should have 300. Huh? No, we don't. Why? Okay, what did I do? Which, okay, so then we should now have it, I guess. Okay, good. So this is the push to talk. Yeah, okay, so yeah, this is the push to talk, and then this is gonna be the power button. Like this, and also 300 microns from the edge. Nearly. Like this. Okay, so the buttons are placed now. However, I don't think we have 3D models for the button. Gonna have to look it up. It's Worth Electronic. Yeah, I contacted them to know if they had any license on their 3D files, and they never got back to me. So I guess it's one more file that we are not supposed to be able to use. So this is the button, what it looks like. And so we see that we have 2 steps that are gonna go in the holes in the PCB, and this is better than no steps because it's gonna improve the mechanical strength of the assembly, so that when you push on the button, it's not only the solder joints that take up all the effort that you put in, it's also these steps which are gonna be more robust, I guess. So yeah, maybe, I don't know, Jay, yeah. Did we want the button to line up 25 millimeters the same? What do you mean by that? So, oh, what? Yeah, you're right, it's not at all lined up. Yeah, you're correct. It's my bad. I completely didn't see it. Let's go back. This should be 25 millimeters from here. Let's check. It is. And this is completely not. Now it should be okay. Yeah, okay, they are aligned. I'm just gonna, just to be safe, move them inwards by 50 microns. So okay, this should be good. So no buttons are placed. They are gonna be on the bottom side of the board that we are doing. So that means inside, in between the nucleo board and the module board, the proof of concept. All right. Should we try to do the yeah, but now the buttons are opposite to where I intended on putting the power supply. So for the PTT it's not a problem, but for the power supply one, it's I guess we are gonna have to route some traces, but it's not, yeah, not a major issue because we have plenty of room here. We can also do it on the bottom side of the board if needed. No, let's go back to this kind of grid. Yeah, it would be nice if we could have a step model of the buttons. So let me find back the reference and show that to you. Okay, it's this one. I'm gonna put the link in the chat. So if you are able to do, yeah, quick, we don't need all the details of course, but maybe the body, the button and the 4 legs, and maybe the 2 stubs, if you can. The stubs, it's not mandatory. But that would be enough for us to be able, at least for you, to be able to check the design of the case with the step file exported by KiCad. Okay. So that would be amazing if you could have it done for this weekend. Monday I'm gonna have some free time again, so maybe I will live stream, maybe not. I will see what goes on. But then if you have it done this weekend and I do a stream on Monday, I'm gonna include it in the board on Monday. Load switch. Let's quickly, so you won't be able to see it, but I'm gonna place that on the second screen and quickly arrange the passive components around it. Yeah, okay. So like this, so this is the quick output discharge. So when it turns off, it discharges everything. This we don't need. This we need. It's the rise time. So yeah, it needs to connect to that one. And this is the divider bridge, which will allow us to measure the battery voltage. But so yeah, we don't. Let me have a look quickly at this datasheet because I didn't put any capacitor on the input. I'm wondering if I should. Yeah, we should place a small input capacitor. I guess. I mean, yeah, it's always better to have a small one. For the large one, they are near the components that eat up a lot of power. And also, did they place one at the output? Yeah, not really. I mean, it's just a switch, not that big of a deal. Yeah, okay, let's place a small 100 nanofarad one at the input, and then good. And select the footprint. Okay, good. That's done. Okay. We still have to do some things for the loop compensation of the power supply. I'm gonna look at that maybe yeah, whenever I have some time for it, and maybe we can do the final computations in a stream. I don't know who would be interested in that, but yeah, we could do some calculations and show you how this kind of thing is done, because it can be quite tricky actually. Quite a lot of math involved. This is the button controller, and this is more or less where it needs to be. And where should we place that? I guess so. This needs to go there. Come on. I can't get it to go the way I want it. Okay, great. And this needs to go down. Huh. Maybe we should put that near the button, but we are gonna have the RF part too. Oh yeah, and I wanted to invert two things on the RF part. Let's do that now. Basically, the thing I noticed is that RF2 and RF1, if we swap them, the layout is gonna be much easier, so it can be done very quickly. Like this. And let's just get those further from this and give it a bit of space. Perfect. Okay. Which means that now, yeah, this have to be routed right here, which is much easier. Let's try to put it about in the middle of it, of the two. Which would be about this. Let's have a look at the datasheet to see how they route that. Do they have hardware design or something like that? No, they don't. Okay. Let's use our brain for that. I guess if we go in, the thing is, this can't happen. I don't like that. So let's maybe then we can yes, we should avoid having this stub. It's gonna disturb everything. Then we can just maybe use a thinner track. I like this much better. Let's try to do same thing on the other side. Like this. Great. Hey! Hi, French version of Watcher. How was the big antenna on the Champ de Mars? Let me take back the schematic on the other screen and see what I have here. So this is the DC block capacitor for the output, and then we go straight to the semiconductor, like that. So no, let's not use that this way. We are gonna have the same problem here, so let me do that, and then come on, the small freezes are starting to be quite annoying and prevent me from moving things precisely. Okay, DC block capacitor, it's good. Now those are two capacitors that you have to add to the control lines, which are gonna have to be routed to the nucleo connectors in order to select which output we want, which input we want to route the antenna, or which input we want. It's bidirectional. Okay, so those two should be on this side, so let's take a bit of space and shift that a bit. And align that like this. Okay, and then we will have to route the two signals to the nucleo, to the power, this to the power and this to the ground. This one is unused on the middle. Okay, well, yeah, this is gonna be a short stream today. I think I'm gonna go pretty soon, in a few minutes maybe. So this would be placed about here. Okay. And load switch. Okay, so what is left to do on this board is mainly the power supply. We have a lot of things to do for the power supply. Various components, so diode here, solder bridge. We have all these ferrite beads. The load switch, divider bridge, push button controller. What are those? Oh yeah, they are the that we can place it quickly. So they are the PTT RC T-bounce things. So this one needs to be I don't like it this way. Let's drag the via a bit further, like this, like this, and so this will need to be routed to this one. Oh, it's easy. I will do that now. Well, I can actually... the fridges are annoying. Okay. And go up to right here. Good. Well, one more thing connected to the connectors. It's starting to take shape. I like it. All those test points, we are just gonna drop them on the board wherever we have some room for them. It's not really important for the functioning of the board. It's more for us for the debug and so on. Okay, well, let's save this, and maybe I can already export a step file. So I'm gonna just push everything which is outside the board. I'm gonna put roughly on the board somewhere so that we don't have any components which are outside of the board, because it's annoying for the step file. So let's just do a... Oh, can I think KiCad has functionalities to arrange things in grids, and so can I do that? Align, distribute, or create array. So how many do we have? 3, 6, 10, 13, which is prime, so we are just gonna do... No, I multiplied them. I thought I could. Well, let's not bother much. So yeah, those are definitely not in their final location, just so that they are on the PCB and not outside of it when it comes to the step file. Same thing goes for this, which we can place... let's move that to here. Then this can go here, and this can go here. test point, and jumper. So now everything is roughly on the board, and now we can also export step. Great. And so okay, let's place the origin right here. So this is gonna be the 0, 0, 0, 0 coordinates of the step file too. Hey Leo, sorry I didn't see you earlier. Yeah, we can. Yeah, we could modify the test points to be just paths, but it's better if you have some clearance around the test points too, because we are gonna need to access them, I guess, at some point. It's really not a big deal actually. We are not gonna solder anything in, just wires if we need to have access to them. So that's it. Okay, so the board, it's done for today. The schematic, let's save everything and re-plot it. And now we can push our changes. So what did we change mostly in the schematic? Yeah, okay, just I guess we, oh, this one we don't need. Oh yeah, and also like this. This need to go in too. And then we have the PCB and step file. Yeah, let's just put in the comments that oh, yes. And push. Did I push that too? Yes, okay. Well, thank you everybody for today. I'm now gonna go. Wish you a great weekend. And bye bye, I guess. See you I hope maybe on Monday during the day I should be able to do a live stream, but I will try to plan it a bit better and also tell you earlier than today. So yeah, this was a bit improvised today. Bye bye, and see you later.